Morning, everyone. So just a couple quick announcements for the midterm 2. It turned out the question 3 score was not added in the sum. So that's why everyone, it was missing some number. So I fixed that and also updated the percentage in Blackboard. So you should be seeing that now, okay? Another quick announcement is I had to do a schedule change in the office hours. So Wednesdays 3 to 4, I'm now moving it to 12:45 to 1:45. So it's really just gonna be the 1 hour right after our class. So it's also an announcement was sent in Blackboard. Okay, just those quick announcements. Now, if you still notice anything with your midterm, please email me. But so far, I believe I've addressed everybody's concern. Okay, so today we will discuss the electric displacement. We will define a new quantity to calculate the electric field in dielectric material that has a polarization. So we know that other than the free charges, we now have bound charges. In general, if you're looking at a material, you may end up with some free charges and you may end up with some bound charges, right? The free charges are the one you added. You have control over how much free charge to add. The bound charge are a response of the dielectric material to the polarization, to the external E field. So now you end up with both of them, which means your total charge density is going to be the free charge plus the bound charge together. Okay, now these are something you place it yourself, and you have control on how much you want to put. Those are the free charges. These you don't really have any control because those are the response of your material. So if we look at Gauss's law, divergence of E is equal to rho over epsilon naught. Now this rho will include both the free and the bound charges. So it's going to be rho free plus rho bound together over epsilon naught. Okay, and recall the volume density, the bound charges can be rewritten using the divergence of P, right? Polarization P. So this can be rewritten using this plus the free charges over this. So you can see now we have the divergence on the left-hand side. We have a divergence on the right-hand side. We can move them together. Okay, so a few more steps. So what we'll do is we will put E and P over epsilon naught together. And that's going to equal to rho free over epsilon naught. Okay. All right. So we are going to define a new quantity. See, we're defining D to be epsilon naught E plus P. So that you can see we multiply both sides by epsilon naught. Right? The left-hand side becomes this new quantity displacement, del dot D, and the right-hand side has only free charge left, the density of the free charges. The divergence of D is equal to rho F. Okay, so this is our definition. Define displacement D, which is epsilon naught times E plus polarization of the material D, material P. Okay. All right. And you can see the this is a differential format. Now, if you look at the integration format, it's going to be D dot into dA. The flux of D is equal to Q free. Okay. So this is your differential format. This is your integral format. Okay. I'll talk about the advantages of using D in just a minute here. But before we do that, let's look at a question here. So this is what we just did, right? We defined an electric displacement field. We call it the D field to be both E and P are both in it. If we put this dielectric material in the external field, E external, and it polarizes adding the new field, right? The new field that's due to the bound charges are the E induced charges. So and these two superposition become the total E field, right? So in our definition, this little E right here, what do you think this E represent? Does it represent the external field or the induced field or the total field? So I'm going to let you go ahead and vote on this. Okay, all right, just 5 more seconds if you haven't voted. Any last minute vote? Okay, I'm gonna go ahead and close this. Let's take a look. All right, so to look at the format of, okay, epsilon naught E plus T, right? You might be thinking, oh, maybe it's the external field plus T, that's the polarization, right? Gives you the D. But if we want to figure out what this E is, let's go back to our derivation to see how is D defined. Go back to our derivation. D comes from here, right? And we use the E that's coming from here. And again, what does this E represent? This E represents this E in the beginning. And you can see this E is due to overall charge density rho, right? This E is already including the influence of both the free charges and the bound charges. So it's going to be your total E field. And you moved this to the other side of the equation and you defined D, right? So you can see throughout this derivation, we notice this E is really the total field. So C is correct. Very good. Okay, so why do we want to define a D field? By looking at this, these two equations, you probably notice that the right-hand side is easy to calculate. It's also something it can be easily known to us. The free charges are something you place yourself, you have control over. Rho F or the free charges, these are externally determined, which is easy to calculate. So you know what it is. So which makes D easy to calculate if you have the symmetry to use Gauss's law, the similar format for Gauss's law, it's easy to calculate D. So if we can easily calculate D and go back to look at the definition of D, if you already know polarization, then you can calculate the E field. So you're able
Dr. Ryan?
Yes?
What do you mean by externally determined?
Externally determined meaning it's not a response from the material. The material like rho bound. These are the bound charges. Those are a response of the material to a outside influence. Those you don't know, you can't see it, right? Hard to measure. Right. Rho free is you can simply inject a charge on. You can dump some charge on the material, so you can decide how much to put, right?
That's okay. Got it. Yeah, that makes sense. Thank you.
Okay, thanks for the question. So you can, by calculating D first, you can calculate E, and you know where the E field is. Okay, so, but also the type of material that later on we will discuss, polarization. We're describing a particular type of material that's polarization is also easily calculated. Otherwise, we still could not find E. Okay, but with those two conditions, is that you calculate D first if you have the symmetry, and also P is not too hard to find, and then you can find the E field. So let's look at one example. Okay, so what do we have? We have a sphere. Those are dielectric. So it's not a conductor, right? It's just a non-conducting material with a sphere. And you injected a positive Q, that's the free charge, right? This is the free charge that you have control over, and you placed it at the center of the sphere. So you can see the sphere is now going to be polarized due to the positive Q. There are no other free charges elsewhere. So what is D? Let's calculate it. Okay. Right. Okay. This is a direct application of the equation we just derived. So take a look at D dot into dA is equal to Q3 and see what answer would you come up with. All right, 10 more seconds. Okay, any last minute vote? All right, if not, I'm going to end this and let's take a look. Quite split between the choice A and C. Okay. It might be reasonable to argue, well, inside the material or outside the material, perhaps it should make a difference, right? The E field does. We know that when you have a conductor or dielectric material, we always calculate E inside versus outside. So perhaps the inside and outside should make a distinction, right? So that's quite reasonable. So anybody would like to share their thoughts with us? So it looks like the difference between these two expressions are off by a factor of so not. So anybody would like to say more about the answer choices? Which one do you think is right? Or do you think it doesn't matter? It should be the same expression everywhere?
So I think that specifying where you are inside and outside the circle doesn't matter. And the reason being is because if you come up with D as a function of R, if you are at the boundary of your sphere, you could just simply plug in big R for little r. In other words, the equation we have is general. Why there's a factor of 1 over epsilon naught in there, I don't understand why.
Okay, right, very good. Thank you, Sebastian. Look at this expression. You see that the unit for D is D times the area. The area is going to be meter squared, R squared, is equal to Q. So that's the Coulomb. So you can see that this one will give you some extra units, which is not matching up with our previous equation for D, right? So if this one is saying that, well, it's only going to be decided by the charges. So if you enclose a smaller circle, it's enclosing Q. If you enclose a bigger circle, it's still enclosing Q. It doesn't really change. So that when we do the calculation, it's really going to be the same no matter where you are, because inside or outside is all Q. So D times 4 pi R squared, regardless how big of your circle is going to be Q. D is going to be 1 over 4 pi epsilon naught Q over R squared. Okay, so that is, so A is correct. But it makes sense to think maybe the inside and outside should make a difference. There is a difference. The difference lies in E and P. P and E are different depending on where you are. You're inside or outside of the sphere. So now let's look at what those two are going to be. Okay. Before we do that, anybody can tell us the direction of D? Here we calculate the magnitude, but what about the direction? D is pointing in which direction?
In the R hat direction?
In the R hat direction. And how do we know that?
Well, R represents the distance from the origin to your point of interest, which is always along a radial line.
Yes, R is the radial component. And you probably already figured out that D is in R hat when you did the dot product to simplify your integral, right? You already know D and dA are in the same direction, therefore you can get rid of this dot product. You know it's in the R hat direction because D is in the same direction as E. So E field for this is going to be the radially outward. So D must be radially outward. And because they are all in the same equation, then there must be P is also radially outward. Does that make sense that polarization is also in the R hat direction? How do we figure out the direction of polarization?
Isn't it in the same direction as E?
It's in the same direction as E. Thank you, Benjamin. So if you have an external E field here, your P generates an E field. I'm going to draw it. It's going to be radially outward, right? This is where the E is going to be. And under this influence of the E field, you can see the dipoles inside the material are going to align themselves, where negative are going to be at this end, positive going to be the other end, right? Negatives are here, positives are here. These are little bound molecules. They're all going to be lined up like this. And a dipole moment, a little p, is in the direction from negative charge to positive charge, from negative to positive, right? So it's in the r hat direction as well. See that P is also in the r hat direction. So there is no conflict. D is going to be in r. Okay, and D is everywhere the same, regardless if you're in the material or not. So for outside, let's look at the outside region. Outside, what is polarization outside? Is equal to outside of the sphere. Do you have any polarization outside of the sphere?
I would say no, because all the charge is on and in the sphere.
Yeah, because you're polarizing the material. Outside of the material, obviously, you're not polarizing anything. The material is not even there. So polarization is 0 outside, which means, okay, if D is the same everywhere and P outside is 0, now I can calculate my E outside. E outside is going to be D over epsilon naught. So E is going to be 1 over, hold on. See, I added epsilon naught. Oops. 1 over 4 pi r squared over epsilon naught. You can see this is something you're very familiar with, right? 1 kq over r squared. This is just a Coulomb potential. This is just a E field due to a point charge. You already know that, right? Is in the r hat direction. So we calculate this by doing the D first, and then you found the E outside of the sphere is really just a point charge potential, E field. Okay, so inside E must be different, I think, because now you have polarization. So for inside, the E is now going to be D over epsilon naught minus P, the polarization inside. Okay, so this is still KQ over R, but you can see your E field now is being reduced because you have a polarization, you have an induced field, and inside is going to be less than the outside. So it's going to be less than the KQ over R squared, smaller. But we need to know what exactly the polarization is. We need to know what kind of material it is before we can calculate the exact expression for E inside. Right? But here, what we can see it's going to be a smaller E field, a weaker E field inside. All right, so it turns out the inside and outside have different E field, you have different polarization, but D is the same regardless if you're inside or outside. So this is a quick example of showing how we use displacement field to do our calculation. But we need to know P, right? The answer, the take-home message here, we need to know how to calculate before we can do the E, solve everything. Okay.
Dr. Ryan, we were referring to D as your displacement field, displacement vector.
Mm-hmm.
So is it a physical quantity or is it just a variable that we defined?
It's a very good question. I was going to talk about that. The thing about D and E, we need to be a little bit careful because if we see this, we might be so jumping upside down thinking, great, now we can always just calculate D, right? It's so much better than doing E because all we need to know is the free charges. Q3. As opposed to Gauss's law for E is Q over So this Q includes free and displacement and bound charges. So one might argue, well, isn't as long as you have free charge, you can find D. But the problem is the relationship between free density and D is not like how rho decides E. Okay, rho, as long as you know your charge density, you can uniquely determine E. Always find E, no matter what method you use. You might use sometimes when symmetry allows, use Gauss's law. If not, sometimes you can do the Laplace equation, sound equation. You can always find E. But the relationship between D and rho free is not really like that. So this one tells you whatever this is, you can always find your potential. Also, of course, you need to set up some boundary conditions for the potential, of course. However, implicitly inside this equation, it tells you how do I get this equation? I said because the curl of E is always 0 for electrostatics, okay? And from math, we know that the curl of a gradient of some field is always 0. Therefore, I can always find a potential to define my E, right? I can always represent E using a potential, a scalar, and that is the potential V.
Mhm.
And then you can rewrite your Gauss's law using your V. It comes like this. However, the curl of D is not necessarily always 0. The curl of D is determined by the curl of E as well as the curl of P. Curl of E is always 0, but curl of P not necessarily always 0. So the curl of D is not always going to be 0. So we're not going to end up with this equation where you can always find your electric field. So you can calculate D when symmetry allows. Later on, we will do an example. But it's not always the case. So to answer your question is the displacement D is a mathematical tool. It does not have as fundamental a physical meaning as your E field is. It's really just a mathematical tool.
Okay. Okay, thank you.
Okay, so before we move on to do more problems, have another couple of side comments. So let's continue with our discussion here. Like that page. Let's not lose it. Oh. Hopefully I've added it. Where's my page? Okay, sorry about that. Okay, so let's review a couple boundary conditions. Then we will have some boundary conditions for D as well. So boundary conditions. This is our surface. And I draw a little cube. Okay. And here at the surface, you have some surface density, rho or sigma. And you may have some E field above the surface, and you may have some E field below the surface. And from Gauss's law, we can apply Gauss's law to this Gaussian surface that we just draw. So you have a top surface and a bottom surface, and the A is in this direction, right? This is your n hat. So I will have E above dot into n hat times area minus E below dot into n hat area is equal to Q. So Q is going to be sigma A, right? Density times area over epsilon. Okay, now you can see that the n hat dot into n hat picks out the perpendicular component, right? Because it's a dot product. So I can write this using E perpendicular above minus E perpendicular below is equal to sigma over epsilon naught. I get rid of, canceled my A. So this is the one of the boundary conditions you have already seen in the previous classes. We can do the same thing for the parallel component. So for parallel component, I'm going to draw a loop. Instead of a surface, it's going to draw a loop. This way, this way, this way. So you have, again, E below. You may have some E above. We know this because the curl V is always 0. This is for static field. This can be transferred into this language because of Stokes' theorem. Right? Stokes' theorem saying the curl of E dot into dA dot into dA is the line integral of the EDL. So EDL is always 0. So if you evaluate your E dl, so you can see this will pick out the parallel component of E, right? Because dl is parallel to your surface. So you need E parallel above times the length L minus E parallel below times length L equals 0. So this will tell you the parallel component of E is always continuous. This is again something we have done. Maybe not too much detail, but we briefly mentioned it in the previous chapters. Okay, so this is saying parallel component of E is always continuous. The perpendicular component will experience a change, especially if you have a surface going through a boundary with surface charge on it. You're going to experience a change in your E field for the perpendicular component, but not the parallel component. Okay, so these two we already know. So those are the usual boundary conditions we have seen previously. So here, what do we do if we have the D field? Here we have do the same thing. Okay. We need some free charges. If we have some free charge density here, and you may have D below, you may have D above. So using the same method, you can see that this will reduce into D above minus D below. The perpendicular is going to be sigma F, okay? Because this is F. This is about the D field. So this might be helpful when we find D. So if you know the charge density, especially if you know the free charge density, you can apply the boundary conditions and help you find D. That's one of the boundary conditions that might be useful. And again, you might wonder, what about the other one that's equivalent to the E dot into dl, but here we have D dot into dl. D dot into dl, you can see D is epsilon naught E plus P, but the integral of D E dl is always 0. So this is going to equal to only P dot into dl because E dot into dl is 0, right? So equal to P dot into dl. So from here, you can derive another boundary condition that tells you, okay, D parallel above minus D parallel below is equal to P parallel above minus P parallel below. It's really just by working out the line integration, right? Okay, so you got something, but again, you can see we cannot get around by calculating P. We still don't know P. What is P? We need to find out. So that's the next discussion is we are able to solve a particular case of materials when those are linear materials. So this is a model that we defined to make this calculation a little bit easy to solve. So let's take a look at that. So there are type of dielectric materials. If they are linear, so we can solve them more easily. If they're linear, meaning that the polarization is proportional to the E field. And polarization responding to your external field in a linear way. They have some constants right here. Okay, so we call these linear dielectric. So P is if the material obey these features, P is epsilon naught times chi E times the external E field E. So usually the electric susceptibility constant is usually very small and is always positive. So if you're talking about different materials, we can think about the different limits it may have, right? So what if we have conductors, okay? Because when we're talking about dielectric material, we can think about the different extremes, something that's like a conductor, or something is barely polarizable at all. So if something like a conductor, what do you think the susceptibility constant will be? Is it more like close to zero, or is it more like infinity? Or if you talking about material that is really hard to polarize, like vacuum, right? It's really extremely hard to polarize. What do you think the constant has to be? I'll tell you each one of them corresponding to each of these limits. So which one is which? Which one is which? So vacuum is very hard to polarize.
For a conductor, wouldn't electric susceptibility be really high?
Yeah, and why would that be?
Because let's say if you have a parallel E field component near your surface, and the charges will rearrange so that the only component of the E field is perpendicular.
Okay.
In other words, you can more easily polarize a conductor rather than a vacuum.
Yes, so conductors are more polarizable. Very.
So your electric susceptibility is telling you how hard or how easy it is to polarize the material.
Yes, very good. So for a material that's very hard to polarize, the polarization must be close to nothing. It's hard to polarize. You're not going to get any polarization. So you want that to be zero, right? You want the constant to be zero. So this is more like vacuum materials, material that's hard to polarize. So polarization is almost zero, no polarization. However, if you're dealing with materials that's very easy to polarize, like a conductor, then you can see that the susceptibility is almost infinity, because a little E field is going to be a lot of polarization. So the materials are going to respond to that a lot. Okay, so that is the linear dielectric. So for such materials, you can see that we are able to define our relationship between D and E. We can do a little bit more to it. So replacing P using the relationship of P and E, you can plug in epsilon naught chi E and E, and you can take E outside of the parentheses. It becomes epsilon naught times 1 plus the constant. So here, people also define a new constant called the dielectric constant, relative dielectric constant epsilon r. So it's going to be 1 plus pi of E. Okay. So there are a lot of constants, so it can be confusing. A lot of times we need to refer to our notation to see, okay, exactly what this constant is referring to. And epsilon naught is the permittivity for vacuum. So this is for vacuum. So when you put epsilon naught and epsilon r together, again, sometimes it's just called the epsilon, which is the permittivity of the material. So a lot of constants in here, right? We had the chi E and have the epsilon relative, we have the epsilon, so a lot of constants. So it's really just for the sake of sometimes which one is easier for us to calculate, which one was given. We have to go back to our definition to see, okay, what do we know and how do we relate one to another? But you can see for this kind of materials, we are saying we need to know the polarization of the material. And for this kind of material, we do know. We know it is linearly related to your E field. So whenever we solve for our D for such materials, we have solved for our E right away because they are related by these constants, right? So these are one type of material we will do in this class, and they are easily solvable. Okay. All right, so let's go ahead and solve more problems. All right, so now we are ready to use this to solve more problems. Here is one of them. We have a capacitor, a parallel plate capacitor with positive Q on one plate, negative Q on the other. Then you insert dielectric material in between the plates, and it will polarize, right, with negative bound charge on top and positive bound charges on the bottom. So you want to find, let's say you want to find D everywhere. So which equation would you go ahead and use first? I'll let you.
Professor, you said for linear dielectric materials, is P proportional to E?
Yes, it is.
Okay.
Mhm. Okay, I get a question here. Do you get P just from conceptually knowing that the E field must be smaller in the sphere? I believe that was referring to the previous problem. The previous problem, we don't know P. Again, they didn't tell us what kind of material it is. At that point, we don't really know what P is, but we know that E is, as we calculated, is D over epsilon naught minus P. So what we know is E is smaller than the E field outside because there's polarization, right? The induced E field from polarization partially cancel out your external field, but doesn't completely cancel it. So it's just going to reduce your E field to be a little bit weaker than what it originally would have been without polarization. So that's just a quick comment to the question people posed. Okay, I'll let you go ahead and vote on, discuss this actually for a minute. And if we come back, we can vote. Okay, 10 more seconds if you haven't voted already. All right, let's go ahead and take a look. So which of these equations would you head to first? All right. So we're giving a capacitor. We know what the free charges are. Those are the big capital Q, negative Q. And we want to find D everywhere. Which of these equations allow you to find D? Majority of you guys think it's 2, right? Yeah. You see that? We do know the free charges, and which means we can go ahead and find our D right away by applying this equation. You're right. So D 2 is correct. And as the approach that we were trying to take is we want to find D first, and we already know the material is a linear material, and then we can find our E inside the dielectric. That's the ultimate goal. But the equation 2 will allow us to find D everywhere right away. You're right. Okay, so E is correct.
Dr. Wright, are we treating this like Gauss's law in the sense that we enclose our free charge with a certain shape?
Exactly. This is what we're going to do next.
Okay.
It's like the Gauss's law we had for the E field, but now we're doing to our B field. So
And so then it's just weird. Like, how would we figure out which
shape?
shapes, no, not what shape to use, but what situations we can use a shape. Like, for instance, if we were trying to use like if there was a cube that was conducting, emitting an electric field, like we couldn't enclose that with another cube because we know that the E field isn't symmetric about the surface of our Gaussian cube. But here, if D is a mathematical tool, like how would we know which Gaussian surface would apply to, I don't know, a given scenario like what we have in front of us?
So D is a mathematical tool, but we already talked about D is in the same direction as E. So situations where we could have applied Gauss's law for E, we could do the same thing for D because D has that symmetry. You can find a Gaussian surface so that D is
Got it.
in the same
Okay.
direction. So this is exactly what we're going to do next. So this next question is asking, okay, you said you want to find D, let's do it. And let's draw the Gaussian surface for you. Okay. In this Gaussian pillbox that's shown here, the dashed box, we want to know what is D, and then we have to figure out what is a free charge enclosed. What do you think the free charge enclosed in this by this particular Gaussian surface? Okay. I'll let you go ahead and have a little bit discussion on this. One second. All right, 10 more seconds. Any last minute vote? All right, let's take a look. What is the total free charge enclosed? Okay, all right, so we can see that there's the sigma F, the sigma B, right? So in this pillbox, it seems to be capturing the top plate and the top surface of my dielectric. So yes, I agree in terms of the charge is enclosing. You have both of these are included in your Gaussian surface, but we only want the free charge. Which one of these is the free charge?
Sigma F.
So sigma F means free, right? What does B mean? What does this B mean?
Bound.
Bound. So if it's bound, then it's not free, it's bound. So sigma B is a bound charge, does not come into the picture, right? You only care about the free charge. And that's why D is easier to calculate because these Q are what you put onto the conductor, capacitor. You have control over how much. These bound charges are response to your external field by your material. So you don't really know what it is yet. So the total charge, the free charge enclosed is A sigma free times area, right? Okay, so it's A, you don't have to worry about the bound at this point. Okay, so now the next thing is we have to calculate D. We already know the right-hand side to this equation is sigma F times A. And how do we simplify this left-hand side of the equation? So let's look at this pillbox. When we do Gauss's law, we say, okay, we need to look at all the surfaces, right? You have your top surface, you have your bottom surface. This is your little area vector, D is now up and down, perpendicular, right? D is going in the same direction as your top bottom surface. So that's only two surfaces you need to worry. You don't have to worry about the side surface, the front and the back. So just the top and the bottom. Okay, so which means this entire integration will simplify into the top surface times A dot into A, okay, plus the bottom surface dot into another area A. I'm not reducing the dot product just yet. So look at the top surface. The top surface here is inside the conducting plate. These are metal. This is metal, right? So what is D here? The D at the bottom surface are the D inside the dielectric material. This is inside the dielectric. This is inside the metal. What is D inside metal? Because we want to find D in the dielectric. We're just interested in this, but this also enter into our equation. So how do we find D inside the metal? Okay, what is D inside metal? Go back to our definition. D.
Epsilon naught E plus P.
Yes, okay. So what is P inside the metal? What is electric field inside the metal? What is electric field inside the conductor?
0.
0, okay. And what about the polarization inside the conductor?
UD.
One might want to go back to this to think about this. Yes, if you want to go back to this saying, oh, you just told us the polarization is linear proportional to E, but I don't think
It's also 0.
It's also 0. Okay, I did tell you E is 0 inside conductors, but I also told you this is infinity for conductors. So now you got yourself into infinity times 0 situation. So mathematically, it's not very conclusive. So is there another way we can describe polarization conceptually what it should be inside a conductor. You're right, it is 0. I'll release the mystery, it's 0. But how do we convince others that it is 0?
Is it because they're free charges inside the conductor, so they can't really polarize because they're free. They don't have anything to attach to polarize.
You're very good. Yes, excellent. That's a great answer. These are conductors. They're free to move. If we go back to the definition, again, the definition for P, polarization is what? Add all the little dipole moments divided by volume. This is what we define polarization. So you can see that you adding up all the dipole moments everywhere. So polarization is a local quantity. You have to look at individual places inside the material to see if it has the dipole moment. But conductors, no, we don't have those little dipole moments inside conductors because these charges would have moved far away from each other because they can, and they're free to move. So locally, you're no longer going to have these little dipole moments for a conductor. So overall, of course, the overall polarization is 0 because it's not there to be polarized, right? So P is indeed 0 for your conductors. So therefore, D is 0 inside conductors, which make this top part goes to 0. So that just simplify our calculation. Right? The left-hand side is left with this one already. The left-hand side and right-hand side, we also just did it. So I think now you're ready to calculate the D field. We already did this. So now you're ready to calculate what is D in the dielectric material. We have calculated this to be D in the metal times A, which is 0. And another is D in the dielectric times A is equal to Q3. So from this, you can see that we can calculate our dielectric D. D field is sigma F. Okay. All right. So we found D. The next step is we still interested in finding the E field. Okay. So what is the E field inside? And I told you this is a linear dielectric. Okay. So how is E and D related? I'll let you vote on this. I don't think this is gonna take a long time because you just have to refer back to our notes to see how E and D are related for linear materials. D is equal to F naught E plus P. Let me get rid of the vector sign because they're all in the same direction. And for linear materials, P is also equal to linear related to E. Okay, 10 more seconds. Okay, I'm gonna go ahead and close this. All right, yes, very good. So a quick referral to back our notes. We can see B is indeed the correct answer. Very good. We just need to do a little bit substitution. So we can find the electric field inside the dielectric. And we found our D to be, let's go add our D in this picture. So our D calculated to be sigma F. So E is now D over epsilon naught epsilon R, which is sigma free, which are here, over epsilon naught epsilon R. So these are the E field inside the dielectric, and that is E total. If you wanted to represent sigma using Q, it's Q over area, and it is pointing in the, let's call this the Z direction. Okay, and then you can also find what the polarization is. E total. Plug in these quantities in the Z hat. Epsilon, epsilon naught cancel out. Q over A chi E, 1 plus chi E, in the Z hat direction. Okay, I can call this the sigma. It's the sigma, the free charge. So with the polarization, you can calculate these bound charges, right? Because to remember, the bound charges is defined to be P dot into N hat. So on the top surface of the dielectric material, we have these negative bound charges, and these bound charges are now going to be sigma times chi E, 1 plus chi E. Okay. So positive sigma at the bottom, negative sigma B at the top. So you end up with these, and the polarization is going to be pointing in this direction. So for D, for P, or for E, you can see they're all related, which means if the problem can give you either one of them, you can find the other. If they give you D first, well, certainly you divide your D by this quantity, you get your E. And you multiply your E by this quantity, and you get your P. And vice versa, if they give you E first, you can find D and you can find P. Or if you give you polarization, you can find the other two quantities. So as long as we know this is a linear material, any of these information, they can give you one of them, you can find another, right? So for example, if they don't give you anything out of these three, instead they give you bound charges, which means if they give you bound charges, you know what P is because those two are related. So you find polarization, now which means you can find your E field and you can find your D if you wish, right? So these three, as long as you know one, you know the other ones. But it really has to satisfy symmetry. It doesn't always, we don't always have the freedom to do things we want. Now, for example, if you have such a donut-shaped dielectric material, again, you put a free charge in the middle, and you can see that these material will be polarized, right? So it will be polarized with some negative charges here and positive charges here. And can you find your D using this equation? And let's look at this. Can we find D using this equation? So, which means we need to have the proper symmetry. We need to know that D is in the same direction as your dA, parallel to your dA vector, so that we can get rid of the dot product. So for this kind of symmetry, do you think D, we do have the symmetry to allow us to compute D from the Gauss's law?
Wouldn't they be 180 degrees from each other since D points in the same direction as P, which it looks like it would be radially inward since it goes from plus to minus, but I'm not sure.
I'm sorry, can you say that again?
Well, I was thinking that because I know that D is in the same direction as P, and I was guessing that P is radially inward since it goes from plus to minus.
Oh, P is in the same direction as your dipole moment, and dipole moment is from minus to positive. So P is going to be radially outward.
Oh, okay. I switched it in my head. I was thinking of the E field vector.
Yes, so E is also radially outward, P is outward, and your D is indeed outward. So D is outward. And for dA, when I say parallel, yes, it can be 0 degrees or 180 degrees. We all consider them parallel to each other. So dA, right, is this way. So yes, you can calculate your D field using this divergence. Well, the integral format of that is your Gauss's law. Yes, we do. We do have that symmetry. However, I don't have time to do this, but I want to show you, well, if you cut this in half, now you don't have that symmetry anymore. The charge distribution and you have on the edge effects are going to be very complicated, and you couldn't do that anymore. So this one, you don't have this. If you don't have a full sphere, you no longer have that symmetry, and you cannot calculate this using the Gauss's law. Okay, for the little bit 1 minute left, I want to mention a little bit about our pre-lecture that you have just done. So here we have the surface, and you can see due to the surface charge, you will have an external E field, right? So this is your E field. This is your E field in space, and you may have an different E field inside the dielectric material. So a similar question to that is here. Here you have these free surface charge here, and you have some dielectric material here and here. But outside of the material here, on top of the material, you have an E field. And what is the E field? One might argue, well, could it be something smaller than the E naught? Didn't you tell us that the dielectric material induce an E field that partially cancel out the outside of the field? So if this is not here, you're going to have this E field, but this is here is going to reduce your E field. Shouldn't it be smaller? Well, you have already done this, right, in your pre-lecture, so I was just curious what you have answered there. Any thoughts? So do you think this E field is affected by putting two dielectric materials close by? Well, since we're at the time, I will tell you, no, it's not. It's going to be exactly the same as E naught because you are not inside the dielectric material. The E will be reduced only inside the material is smaller. Polarization is only happening inside the material, but not outside. So outside, you're going to have exact same field. So which means going to this question you have already done, your E here is just going to be epsilon over 2 epsilon, sigma over 2 epsilon naught, like using Gauss's law. Here is exactly the same, only inside the material is going to be a little bit smaller. Okay, outside of the material is just the same as before. And it exactly, you can apply your boundary conditions throughout the surface. You can see your perpendicular E field now have a jump. And that is okay because you're passing through some bound charges. You pass through a surface charge, your E field is going to have a jump, and that is okay. Okay, so I just wanted to mention that the E field is only affected inside the materials. Outside of the material is still the same as before as E naught. All right, so that's all we have for you today. I will be going to head over to my office hours shortly. Just give me a couple minutes, but if you have questions, I'll see you there. All right, if not, and I'll see you guys on Friday at our recitation. Bye, everyone.
Thank you, Brian.
Thank you.
Thank you. Bye-bye.